We present FlowNav, an image condition policy for autonomous navigation that relies only on a single wide-angle camera. Effective robo-navigation in unseen environments requires precise control actions at high frequencies. Classical methods have been successful in several scenarios but have trouble generalizing to unseen cases. Recent work using diffusion policies tries to address this problem by creating visual navigation foundation models, but despite their promising results, are computationally expensive and suffer from weak perception. To address these limitations, we present FlowNav, which uses conditional flow matching for action generation and leverages depth priors from depth estimation models. Our model beats the current state of the art in both accuracy and runtime efficiency. We aim to learn a navigation policy pi. The policy should be able to sample actions given observations. So given a set of images, it should be able to sample trajectories for navigation. However, this distribution is intractable. CFM can help us learn a mapping to this distribution. We want to learn a flow or velocity u that can help us move from some known distribution to the target distribution. We learn this using a neural network v theta that regresses to the flow u using a simple loss function. Since we want to sample actions given observations, we change the flow and action sampling accordingly. Once the flow model is trained during inference, we integrate the velocity using the Euler method to move from sample noisy waypoints to the trajectory conditioned on observations. Unlike diffusion, CFM can create straighter paths to the target distribution, making it more efficient. We now move to the architecture that can help us learn the flow. Given the observation images, our aim is to output the flow that can generate the trajectories. We pass the images through an efficient NetB0 encoder. We also pass the image through a depth estimation network to get the depth priors. We use the DynoV2 embeddings from Depth Anything V2 model. These embeddings also help regularize the model and improve the accuracy. Optionally, we also pass the goal image encodings if you want to navigate to a goal. The concatenated embeddings are then passed through a transformer to generate the context embedding. This context is then passed to both the temporal distance prediction head and the flow prediction network. The flow prediction network is a 1D unit which takes in time t, partly denoised action, and context for conditioning. It then outputs the flow at time t. This flow is then used to generate the trajectories during inference. We run extensive experiments on real robos in environments with varying range of difficulties. The aim of our experiments was to measure the robustness and runtime efficiency compared to the baseline. We find that FlowNav has higher accuracy and lower collisions compared to the baseline across the board. The robustness is due to our ability to leverage the depth priors effectively using CFM. We also show that since CFM requires fewer steps to generate valid trajectories, we are much faster than the baseline. FlowNav is thus faster and more accurate than the state of the art. For further details, please refer to the paper. Thank you.